Bill Snodgrass. In this episode of World Around Me, we've got hot stuff, MC Delta T, we got all kinds of stuff going on. And we're gonna make some water boil, and we're gonna have energy. It's all kinds. This is gonna be crazy. This is gonna be great. You're gonna love it. All right, the equipment is very simple. I have a copper sample, a sample of copper. I have a thermometer. I have a styrofoam calorimeter. I have a heat source. We're gonna heat this up. The boiling water is part of other experiments, but in this video, it's just it has no purpose in the video. In my classroom, when you see boiling water on a hot plate, you know the hot plate's hot, so it's a kind of a semi-safety consideration. Plus, we're using it for two other labs that we're doing simultaneously to this one. And so I think I'm ready. I got my calculator. I got something to take notes with. Batteries charged, fully charged. So what we're gonna do, we're gonna get this very hot. We're not gonna put it in the boiling water. We're gonna put it directly on the hot plate. It's gonna get very hot. We're gonna have water in the calorimeter. We're gonna know the mass of the water and the temperature of the water. When we put the very hot piece of copper into the water, some of the water is going to boil and the steam is going to escape. And the rest of the water is going to then participate in absorbing the energy from the hot sample. We're going to use the specific heat of copper, the mass of the sample, and the final temperature of everything, and calculating the amount of water that was converted into steam, which is going to be a lot of energy is going to go there. We're going to predict the initial temperature of the metal sample. So this should be interesting. There's a lot of math. There's not as many measurements as there is math to do, and so the procedures and the data collection part, procedures and results, are going to be relatively simple. And then the conclusion, which is the conclusion will be determining the initial temperature of the sample. The conclusion is going to be very mathematical. And so you say, why would we ever want to do this? Why is this even a thing? Who would want to know this? There are probably many situations where you need to know the initial temperature of something. For example, you may be like sitting in your backyard and a meteorite comes out of the sky and lands in your swimming pool, if you had a swimming pool. Or it may like land into the snowbank if you're living in this area. And there's a explosion of steam and water and stuff if you had a swimming pool. And then you wanted to figure out what the initial temperature is. That's kind of stretching it. A meteorite comes out of the sky and lands in your swimming pool. That's kind of stretching it. But it's a good lab, and it'll be kind of fun. So we're gonna do that. Plus, everybody wants to put the hot thing in the water and watch it sizzle. Watch it sizzle. Who doesn't want to see that happen? So we're gonna do that. Let's get started. First of all, we're gonna find the mass of the sample. I got my scale back here. Going to the mass. 69.56. 69.56 is the mass of the sample. I'm writing that down. 69.56. We're doing grams and joules. So 69.56. That's the mass. I'm gonna go put it on the hot plate. I'm using the tongs because I don't want to, burn myself on the hot plate. So I'm going to put this on there with the tongs. All right, so the sample is directly on the hot plate. It's going to get very hot. I'm going to get some water. First, I'm going to find the mass of the empty cup. 2.13 grams. 2.13 grams is the mass of the empty cup. I'm going to put water in sufficient to cover the sample. And I'm going to find the mass of the water. That's way more than I need. That's enough. Poured some of it out. So now the mass of the cup and the water is 107.26. 107.26. So, if I put the sample in cold, the mass of the cup and the water and the sample would be the sum of all those numbers. But since some of it is going to convert to steam, the actual mass is going to be less than the sum of those numbers. And that difference will be the mass of the steam. So the mass of the steam will be what should have been here, and then subtract from that what is actually here. The part that's missing is going to be the mass of the steam that went out into the atmosphere. Then that will be all of the data that we need to collect. We will have the final temperature of the water. So we do need the initial temperature of the water because that MC delta T thing, the MC delta T thing. The final temperature of the mixture will also be the final temperature of the metal sample. I'm writing that in. Letting this come to equilibrium. We call it I'm going to call it 19 degrees. Initial temperature of the water. (19 degrees). We'll let this sit for a minute. We'll come right back. All right, we have a hot metal sample on a hot plate. It's gotten hot, and we don't know the temperature, but we know the mass. We know all these masses. And what everyone wants to see the sizzle. Here goes. When I'm doing something like this, one of my things is I like to make sure that my left hand doesn't accidentally just like take over and do something I don't want it to do. So I'm not, because I don't want to, burn myself on a super high, like probably hundreds of degrees Celsius. So I've put my left hand behind my back. I've actually looped it through my bell loop just so I'm going to grasp it firmly. If I drop it, I'm just going to back away as a safety precaution. But I didn't drop it until then. Some steam escaped, and the water temperature is going up. We're going to leave the safe zone, I call the hot zone. We're going to go back to the paper and pencil, taking the calorimeter with us. All right, everyone likes the sizzle. The sizzle is done. Now we have to grind out the math. We have to grind out the math. Final temperature. I think you can probably see it. I'm going to make sure the final temperature is 31 degrees. Hopefully we can see that. 31, I'm calling it 31 degrees. Final temperature of 31 degrees. Final temperature is 31 degrees Celsius. 31 degrees Celsius. That's the final temperature. All right, now we need to find the mass of the cup, the water, and the sample. The actual, and now it should add up to the masses that we took before. So we had the mass of the cup and the water at 107.26. And we added 69.56 grams of the sample. So the mass of the cup, the water, and the sample should be the sum of those two numbers. So we're going to go find the actual mass of the cup, the water, and the sample. And the difference between those numbers will be the amount of steam that was produced and lost, and it took off all of that, all of that heat of vaporization energy. So we're going to go find the mass of the cup, the water, and the sample. And it's the actual mass, not the mathematical version. So we're going to go find that mass. 179.65. 179.65 is the actual measured mass of the cup, water, and sample. So as I said before, the mass would have been, had we not created steam, the sum of the cup, the water, and the sample. And the actual mass is less than that. So the difference is the amount of steam that was produced. All right, so we need to now move into the conclusion section. This is our results and our setup. If you're doing the lab in class, that is how you do it. You're going to collect all that data. You'll collect your own data. You'll have your own initial temperature of the water. You'll have your own mass of the sample. You'll have your own mass of the water. All of those things will be your numbers, not the ones from the video. If you're doing the lab virtually, you're going to use these numbers and you're going to do the results, the conclusion section yourself. So these will be your results if you're doing the lab virtually. If you're just doing the whole thing video-wise, you want to see the conclusion, we're going to do the conclusion section and we'll discuss that a little bit further. Not a whole lot more to discuss because the setting up the information is sort of discussed at most of the discussion for us. All right. So if you're doing the lab in class or virtually, this is where you stop. This is where you stop and either go do it or go do your results. The link to the lab template is in the video description. All right, conclusion, results. The results, we collect our data, our conclusion. The conclusion will answer the question, what was the initial temperature? What was the initial temperature of the metal sample? So, metal sample. The metal sample. The final temperature, T sub F, for the metal sample was 31 degrees. I'm going to try to keep the math sort of logical and intuitive rather than just like doing some huge derived formula. So delta T would be equal to T sub I minus 31. So if we know delta T for the mass, we'll be able to calculate. We'll just, calculate that. So if we know what delta T for the mass was, well, how are we going to find delta T for the mass? Well, heat lost, that's the metal sample, equals heat gained. Heat lost equals heat gained. MC delta T is going to be equal to the amount of energy that was converted into steam. So there's going to be a mass of water that went from T sub I, 19 degrees, to 100. And that same mass of water went from 100 into steam. So we're going to have the mass of the steam times the specific heat of water, because it went from 19 degrees to 100. So MC, and then delta T for the steam water. We'll call it steam water, plus the mass of the steam times the heat of vaporization for water. Then the water that stayed in the cup, which we're going to call that the mass of the water. It was just water, times specific heat of water times the delta T for the water. A lot of math over on that right hand side. We have all of those numbers. This is going to end up being a number. We have the mass over here. We will find delta T over here. We'll find C. We'll look it up. That's what we're going to do. That's what we're going to proceed. All right. That's the direction this math is going. We need to Google, and we need to find the specific heat for copper. I'm going to go do that now. All right, the specific heat of copper is 0.385. All right, let's start plugging in some numbers here. Got my scratch paper up here. I'm going to rewrite my formula. Energy loss equals energy gained, Q. M of the sample, C of the sample, delta T of this, and we're going to be calculating. That's the number we're going to be calculating. Equals. All right, back to the scratch paper. Over here we have final temperature was 31, initial temperature was 19. If we subtract those numbers, we get 12. So delta T for the water is 12. Delta T, we're calling that delta T for the water equals 12. The water that became steam, the final temperature for the water that became steam, so we're going to call that the delta T for the steam water, is 19 to 100. So that is 81. All right, specific heat is 4.128. And now we got to do the masses. The mass of the water that became steam is the mass of everything minus the mass that it should have been. All right, so the mass of the steam would have been, calculator, clear, on, clear. So I should have had 176.82 grams. 176.82. If I subtract off the mass of the cup and the sample, now if I take the mass of the cup and the water and subtract off the mass of the cup, that's the mass of the water that I started with. So I have 107 water at 1.3, 107 point water 6, the original mass of the water. But some of that became steam. So how much of it became steam? That number, 176.82. All right, now we have all the variables that we need to plug into our equation. Believe it or not, mass of the sample, 69.56 times the specific heat of the sample, 0.385 times delta T is what we're looking for, equals the heat of vaporization for water, 2257. So we multiply all these numbers, add those numbers up. All right, when we add all those numbers up, we get 8,109.56. And on this side, we have 26.78. We divide both sides by 26.78. Delta T equals 8,109.56 divided by 26.78. So delta T was 302.82 degrees Celsius. The delta T was. All right, the final temperature of the sample, the final temperature was 31 degrees. So delta T equals T sub I minus T sub F. 302.82 equals the initial temperature minus final temperature was 31. Add 31 to both sides. 333.82 equals T sub I. There we have the initial temperature of the metal sample sitting directly on the hot plate, 333.82 degrees. That's it. A lot of math. It's an interesting problem. By using the temperature change and the phase change of the water, we're able to calculate the amount of energy that was created, and then using that amount of energy, backtrack to the initial temperature of the metal sample, which was copper in this case. All right, this is probably a pretty long video, a lot of steps, a lot of math, but I think it's pretty interesting. And if that meteorite ever does fall out of the sky into your snowbank or swimming pool, you're ready to figure out what the initial temperature of that meteorite was, assuming that you can measure all the other numbers. So that's kind of stretching it. A lot of math. It's kind of cool. I kind of enjoy this sort of puzzling through. Can we get the math to answer questions for us? That's kind of the whole point of science and math, is to create ways of explaining the world around us. And with that said, we'll get out of here. Thanks for watching. Please click the like button, subscribe to the channel, sign up for notifications, leave me a comment, question, or suggestion. See you in the next one.